Well, hello friends, welcome to this video. In this video, we will be discussing one of the circuit that is useful in providing the Bell basis in producing the Bell states. So, but before that, let's quickly see the tensorial representation of the swap gates. So the swap gates. So you see, this is the tensor for the swap gate. So now what you can do is, first we have to see what wires are going in and what are coming out. So this is a big circuit, so I can write it as this form. So this is what it means. So this circuit, so this is again equal to, I have done nothing, but I'm saying that there is I, there is J, suppose there is K, there is L, so I, J, K and L. But now what is the representation? So this is important, so let's write a swap KLIJ is equal to, you see, this is the delta, this is also a delta. So this is delta KJ, delta L and I. So this is the representative. But why is this swap gate is a very important point. So for that we have to understand the computational, we have to go to a computational basis. So in the computational basis, I can expand this circuit, I can expand this entire thing. So let's see. So this is summation over I, J, K, L. There is delta, two delta functions. And now I have to see that. So there are two indices down. So these must correspond to the bra. And these must correspond to the ket. So this is K, L, I, J. So this order is important. So if I write K and L, then I have to write I and J. So I am reading here. And I am also reading here. So now what we can do is, so now this is equal to, now you see K comes with a J. So it is summation I, J, J, I, I, J. So particularly what is this operation doing? It is taking the qubit IJ and then swapping it, and then swapping the IJ position and changing it to J and I. So this is why this operation is called the swap operation. Now let's look at something that has to do with something called as a CNOT operation. So let's see. So this entire circuit that we are seeing here, this entire circuit is in horizontal representation. We can bring it to a vertical representation by an anti-clockwise rotation to get this thing. Now you see, if I box this entire thing, I have two indices going in and two out, and this is what is the CNOT operation. So I have written here, so CNOT MLIJ is equal to, it is made up of two smaller parts. One is this guy and one is this guy. This guy is called the copy. So this is a copy operation. So the task of it is to copy the bits. So what it does is, copy. The copy operation, it takes, suppose it takes M entries and it copies to N entries. And then there is a summation over the K. So in this case, it is copying one bit to a 2-bit. So it is copying 0 to 2 times this bit. This is a Hilbert space of 2 qubit Hilbert space, and this is a single qubit Hilbert space. So similarly, there is an Xor operation, which is like an activation whenever. So Xor operation is like the dot product. If you do in terms of Boolean algebra, what it means is whenever there is a 0, 0. So if you multiply 0, 0, you get a 0. Whenever there is a 0, 1. So we have to multiply or we have to add, we have to see that. So the Xor operation is, let's see, 1 plus 1 is a modulo, it gives us 0. If you modulo it with 2, 1 0 is a 1 and it preserves that, 1 0 1 is a 1, it preserves that, and 0 0 is 0. So it is the taking the modulo with respect to 2. So these together forms the CNOT operation. And this is the entire circuit of the CNOT operation. These are the tensorial forms. Now what we can do is, we can say how can we represent CNOT operation by understanding what it actually does. So basically, what will this CNOT operation do? Whenever there is a 0 qubit coming here in this lane, it will keep this part unchanged. Whatever there be, it can be 0 or 1. But whenever there is a 1 coming here, this will get biased due to this XOR operator, and it will change this also to the corresponding other part. Like if it is 0, it will change it to 1, and if it is 1, it will change it to 0. So what this means is that the CNOT operation, what it does is, so let's see, so it will take a 0 0. Suppose I have 0 0. It does nothing, it will produce 0 0. If I have 0 1, it will still do nothing and will give me 0 1. But if I have 1 0, then it will be switched on, and this will change this. So what will I get? So I will keep this same. Here I will get 1. And now if I have a 1 1, then it will again be switched on. So I will get this second qubit will go to 0. So this is the CNOT operation that it does, and it can be written in this form, where this X is a 2 cross 2 Hermitian unitary spin matrix, which is the Pauli X matrix. And this identity, this is the normal identity. This entire thing is 4 cross 4 matrix, because it needs to act in a 2 qubit Hilbert space. So now once we know the CNOT operation, we can create a more complex circuit. You see, I have again changed it to a vertical representation by rotating it. So, and this is the tensorial form of this circuit. This circuit is, what is the form of this circuit is, whenever there is a qubit coming in, it will first act with the Hadamard gate, and then it will act with the CNOT gate. This entire thing is the CNOT gate. So now let's see. So first action is with the Hadamard gate. So here there is nothing, that means here there is a tensor identity. So this is the same wire that I was talking about. Ij is delta Ji. So now what we can do is, we can simply take this tensor. This is the Hadamard gate, and this is the tensor identity, and this is the CNOT operation. Now we will do the matrix product by remembering that these all are actually 4 cross 4, but it is easy to represent them in this 2 cross 2 fashion, and this will give us this. So this is the entire quantum gate operation, including the Hadamard and the CNOT. So now let's put 0 0. So 0 0 is of this form, 1 0 0 0. This is of this form, 0. This is a qubit 0, so and 0. So you see, this notation can be a bit difficult, because 0 is simply 1 0, and 1 is 0 1. And this 0 that is there, this is the vector space 0, and but this 0 that I am writing here, this is the state 0. So with those notations, we can act the gate operation on this 0 0 state, and what we will finally end up with is a Bell state. So this is an entangled state, which is the Bell state. So now you can apply this gate to 0 1, 1 0, and 1 1. You will get the entire Bell basis. So this basis is important for performing these quantum teleportation and all those things. So, and we see that this gate, this particular gate is producing this basis, which has a Hadamard gate and a CNOT gate associated to it. So I think that's all for this video. So one thing is the expression of CNOT. Why I have written in this form is particularly because CNOT is a conditioned NOT operator. So conditioned on the first qubit, whenever the first qubit will attain the value 1, we will change the second bit. So these 4 are that, and then you can take a matrix, 4 cross 4 matrix, and you see there is a 0 0, so there is 1 here. This state also remains unchanged, so there is a 1. This state actually flips, so there is a X operator here actually. So this is the CNOT operator. So I think that's all for this video. I guess we can actually work out one more problem. That is, we have discussed this swap operation. So let's quickly see the raising and lowering of the index. Suppose you have a tensor like this, and I have written something of this fashion. So if I put this as I and this as j, then what this entire thing is? So this entire thing is some sort of, this is k, then there is a delta, and this is above, so this is I k t j k. Now you see there is, this delta is actually rising the index of k and substituting it to I. So this is actually t j I. So this index notation is important. So this is t j I. Now you can quickly check one more. We will see that in the next video that these are equivalent classes of these things. There are equivalent classes of these which can be where we raise and lower these indexes using the wire structure. So let's see. So this is I, if this is J, and this is K. What we can write it as delta I K, and there is a T K, and there is J. So this will again lower. This is T. This is T I J. So you see, this thing is a tensorial form of T I J, and this thing is a tensorial form of T J I. So this thing is this, and this thing is this. So that's all for this video. I hope I was able to explain this. So that's all.